Welcome back to CST432. Today we look into a new topic, Split Personality, Part 1. Here we will look into several new ideas. First of all, what is thumb state? Secondly, how do we perform ARM and thumb interworking? And based on this, how do we perform direct interworking calls versus indirect interworking calls? Okay, what is thumb state? Thumb state is only present in the T variants of the ARM processor architectures. What happens in thumb state is that instead of using a complete 32 bits to represent an instruction, we use 16-bit encoding of common instructions. What this results in is that we will no longer have the ability to perform unconditional execution, meaning that instructions are executed always except for certain conditional instructions such as branch. Secondly, registers are divided into low registers and high registers. The reason being that low registers are accessible in most instructions, but high registers are limited to specific instructions only. And finally, many instructions, except for those involving high registers, will update the flags automatically. So this means that we will have the S suffix by default for most instructions. Now, how does this affect our view of the registers? In thumb state, at first glance, there is little change. We still have access to R0 to R7 as usual. In addition, we have access to the stack pointer, the link register, and the program counter. Now, in the user state, there is no difference. But in the privileged modes, there are several changes. First of all, the fast interrupt mode, we do not have the bank registers that we would have otherwise for use in this mode and in thumb state. As well as for the supervisor, abort, IRQ, and undefined states, we only have the stack pointer and link register as bank registers. Now, bear in mind too that in the execution of the privileged states, typically we will be running in ARM mode and not thumb mode unless the program specifically switches over to thumb mode in those states. Here we see the mapping of thumb to ARM registers. Basically, thumb presents a subset view of the registers present in the ARM microprocessor. The R0 and R7 are direct mapping to the ARM mode R0 to R7. There is no difference. The only difference is that R8 to R15 have limited access in thumb state. Now, thumb instructions are very similar to ARM instructions. In fact, using the UAL syntax, the identical mnemonics are used for both ARM and thumb instructions. This makes it possible for us to write one assembly language source file for use whether it is compiled as ARM instructions or as thumb instructions. The only thing to be careful of is that flags are automatically updated for many instructions in thumb state. And secondly, not all registers are accessible in every instruction, and constant arguments have a limited range compared to ARM instructions. This may affect the use of certain inline constants as arguments to an instruction. Finally, there are special or restricted arguments for certain instructions. For example, the push instruction has a default ability to include a link register, but the pop instruction does not allow us to access the link register. It's only possible to pop the value pushed in by the link register to the program counter. Now let's look at the various thumb instructions in more detail. The first group is the data movement instructions, which is move and move S. Now, as we have seen, the default when we're using the move instruction is move S. Move S allows us to initialize the register to a constant value from the range 0 to 255, or else to copy the value from one low register to another low register. Now, if we want to access the high registers or combination of high and low registers, we need to use a different move instruction, which do not affect the flags. The next group of data movement instructions is the load register instructions. Now, the thumb version of these instructions have more restrictions. You have the load byte, load half word, load sign byte, load sign word, half words, but the value in the arguments that you can use are limited, and you must be careful that you do not use the invalid values there. Similarly, there are the store, word, store half word, and store byte instructions. Again, there are restrictions on what kind of arguments or operands are provided with these instructions. The thumb version of load multiple provides only one version, which is load multiple with increment after, and this is mirrored in the store multiple instruction as well. The pop and push instructions are used for stack manipulation. By default, it will update the stack pointer as well as to implement the full descending stack in implementation. Now the next group of instructions relating to integer arithmetic start with the add instructions. The add instructions involving the lower registers are always with the S suffix, so it's add S and ADCS. This will update the flags whenever we perform an addition. Now the add instruction without the S suffix only affects the high registers or combination of high and low registers. There are some special modes for the add instruction that allow us to perform stack pointer based addition as well as PC based addition for retrieving certain values from memory. Now the ADR instruction is actually a special case of loading the constant value from the literal pool stored in memory into a register. Similarly, the subtract instructions have the SUBS, SBCS versions for low register manipulation. The subtract without the S suffix is used for high register manipulation, as well as an additional instruction is given, negate with S suffix, negate S, which allows us to convert a value from a positive to a negative value in one instruction. There's also a multiplication instruction, multiply with the updating of the flag registers. Now the manipulation of bit values and logic calculations in thumb mode is very much identical to those for ARM mode. The only difference is that the flags are updated for each of these instructions, so it always comes with an S suffix. Now in thumb mode, shift and rotate are not part of the operand 2 operation. Instead, they are defined as specific instructions to allow us to perform the shift and rotate operations we take for granted in ARM mode. And of course, once we perform the shift and rotate, the flags will also be updated as a result. The thumb compare instructions are pretty much the same as what is found in the ARM instruction set also. We are allowed to compare negative as well as test against values in other registers, as pretty much the same way we can do so in ARM. Now the thumb flow control instructions are the only type of instructions that allow us to have conditional execution, which is a branch with condition. The other flow control instructions such as branch and link and branch and exchange, which is a new instruction used for switching between ARM and thumb mode, are unconditional. In addition, we still have access to the software interrupt or supervisor mode instruction. Here we have a table showing the thumb instruction encoding, meaning how it is represented in object code in terms of the hexadecimal values that are used. In this table, it is a bit confusing because it lists out the various different instructions that are possible in thumb mode. However, the mnemonic used to represent some of these instructions are converted into a version that is similar, meaning that there may be two different instruction encoding that results in the same mnemonic, such as add, used for PC relative add as well as the normal arithmetic add. For the rest of the thumb instruction encoding, the story is pretty similar. The only thing to note is that the branch and link instruction, shown here as a long branch with link, is actually a 32-bit instruction. This is the only 32-bit instruction in the thumb instruction set in the ARM-40 architecture. Since we have thumb state and ARM state, what do we do when we want to switch between them? This is called interworking. Now, interworking allows the switching of processor state from ARM to thumb or thumb to ARM. Now, this is accomplished using the branch and exchange instruction, or otherwise known as BX. The target address is given in the register or the offset that we use. So Interworking is the process of switching between ARM and thumb state, or vice versa. This is accomplished using the branch and exchange instruction, which is BX. Now, the way we know whether we are going to switch between ARM and thumb state is the definition of the target address for the switch. If the target address is given in a register Rn, the bit 0 of the target address will determine whether it is going to be in ARM or thumb state when after we execute the BX instruction. If bit 0 is 0, it means that the next instruction will be executed in ARM state. If bit 0 has the value 1, it will switch over to thumb state instead. And when we do the switching, the T flag in the status register indicates the current executing processor state and is stored in the SPSR when we enter into exception mode. The reason being that in exception modes, we are always executing the first instruction in ARM state. So when we want to exit exception mode, we must know the previous state where this processor was found in order to return to the correct execution mode. First, we look at direct interworking calls, where we call the routine directly in our software. In such a routine, they must first be declared as interworking routine, whether thumb to ARM or ARM to thumb. Direct call to interworking routine is written in assembly as usual, meaning that we will have the branch and link instruction or BL with the target interworking routine address, usually referenced by the label of the routine name. The assembly language assembler will insert an additional linear code which will make the interworking take place automatically. First, we will look at direct thumb to ARM interworking. Here we declare a thumb function. Note that at the beginning we have the .thumb_func directive to inform the assembler that this is a thumb function. So just take note that if you do not do so, the assembler would not know that this is a thumb function. Somewhere within the routine, we will perform a call to a ARM routine. Now we see here that we are using the normal routine calling process, which is the BL and then the name of the routine. In our case, we just call it ARM routine for simplicity. When we perform the branch and link instruction, several steps take place. First of all, the return address is taken from the label return from ARM, which is the next thumb instruction in the sequence. The return address will have the bit 0 set to 1 to indicate thumb state, so that when we come back from the ARM routine later, we know that when we switch to the return address, the return address indicating thumb state will allow us to switch back to thumb mode. When we compile the thumb routine defined previously, the branch and link into ARM routine instruction is converted to a branch and link to ARM routine from thumb. This is a linker veneer that's added to the output file to allow us to perform the interworking magic. In this veneer, the first instruction is a branch and exchange PC instruction. This retrieves the address which is given by PC plus 4, which is 2 instructions away in thumb state, and use that to execute the next instruction at that location in ARM state. In that location, there is an ARM branch instruction which allows us to branch to the ARM routine that we wanted to call initially. So this has been done automatically in order to allow us to perform the interworking call. Now we shall look at the interwork ARM routine. First, the declaration of this routine. We note that we will have to declare the ARM routine with a .type directive to indicate that this routine is a function. Now this is important because otherwise the linker does not know that this is something that needs to be dealt with as a routine. Now once we enter the routine, we will store the various registers as well as the link register value into the stack as normal, whether using STM or store multiple with the full descending stack, or else we can also use the push instruction, which is the UAL equivalent. Now in the end of the routine, when we are ready to return, we have to be careful. First of all, we will need to retrieve the values from the stack using the LDMFD or else the pop instruction. Now we do not retrieve the link register value directly into program counter. Now this is because when we do so, if we do so in ARM state, we will return to the address given in the program counter in the link register in ARM state itself. The ARM-40 architecture does not allow us to do a switch to thumb state when we pop a thumb instruction address into the program counter. So first we would then pop the values back into the link register in order to make sure that we stay in ARM state. After we retrieve the correct value into the link register, we will then use the branch and exchange instruction using the link register value to return to thumb state correctly. Next, we shall look at how we perform direct ARM to thumb interworking. First, we declare the ARM routine as normal. Then somewhere along the line, we perform the call to the thumb routine as normal, which is using the branch and link instruction, and you just say branch and link to the thumb routine. However, the assembler will convert this into a branch and link to thumb routine from ARM instead. Now the branch and link instruction should store the next instruction address into the link register. Now in this case, the link register, the bit 0 will have the value 0 to indicate ARM state, so that when we return from the called routine, we will resume execution in ARM state. The veneer generated for the direct ARM to thumb call is a bit more complex. First of all, we note that we will need to use a scratch register, the IP register, for storing the thumb routine address. This is stored into the literal pool in memory and is retrieved using the load register instruction from the address given by the program counter, which is pointing to 8 bytes away from the current instruction. And once we have loaded into the IP register, we will then perform the branch and exchange instruction to switch date. Now the value of the thumb instruction address stored in the memory has bit 0 set to 1. This is to indicate that the switch to thumb state is required. The thumb routine that we wanted to call must be defined using the .thumbfunc directive as well. This indicates to the linker that this is a 16-bit instruction set used for defining the routine. The first thing we do once we enter the thumb routine, of course, is to preserve the registers. In our case, we will push the registers that we want to preserve as well as the link register into the stack. Next, at the end of the thumb routine, we will need to restore the preserved registers. This is done using the pop instructions. But be careful, because here we do not want to pop all the values of the registers back into the original registers. Instead, we will first pop the non-link register registers from the stack. The link register value will be popped into a temporary register, here represented by Rx. Rx typically will be R0, R1, R2 and R3 because these do not need to be preserved. However, since R0 is normally used as a return value register, we would use R1, R2 or R3 instead. And once we pop the return address into these registers, we can then do a branch and exchange using the Rx register to switch back to the ARM state. Now this is important because in the ARM-40 architecture, there is no way to do a direct return from a thumb routine to an ARM routine using the pop instruction. Next, we will look into indirect thumb to ARM interworking. Now this is a bit more complex because the move instruction does not store the thumb flag. So we will need to use a branch and link in order to set the thumb flag before the interworking call. Okay, we assume that we already loaded the ARM instruction routine address into a register such as Rx. Now in order to do the branch and link instruction, we want to be able to resume the execution of the next instruction in thumb state. So we would like to place the branch and link instruction at the end of this sequence. In order to reach there, we will need to do a branch to that position so that we will be able to bypass the branch and exchange instruction that is defined. So this allows us to perform the branch and link and then resume immediately with the following instruction address in thumb state, which is the return from call instruction label. we branch and link to the instruction in the address before this. Now this address contains a branch and exchange instruction. The branch and exchange instruction will take the value in Rx and then perform the switch to ARM state. Now the link register already contains the label address of the label return from call. This allows us to return from the ARM function without having to worry about the location of the next instruction. Next, we look at how we perform the indirect ARM-to-Thumb interworking. This is actually a bit easier because we do not need to worry about the link register value. To do the indirect call, we first must load the thumb routine address into a register such as Rx. Now if you have defined the thumb routine correctly using a thumb func directive, then the assembler will convert the thumb routine address that we reference into a value that has the bit 0 set already. Next, we need to keep the link register. Now the link register value is taken from the program counter value, which currently points to the current instruction plus 8, which is 2 instructions away, which corresponds to the return from call label. Finally, we perform the branch and exchange instruction to switch state to thumb state, and at this point we have the correct link register address, return address in the link register, and we will be able to return from the thumb function to the ARM function in the correct state. To make our life easier, we have defined some interworking macros which will define the necessary directives for us to ensure that the functions and the routine calls are done correctly. So this list of macros are used for defining the ARM routines. The next set of macros are used for defining thumb routines as well as for thumb routines to call the ARM interworking routines correctly. What's the future for thumb state? Here we look into how thumb state has evolved over time. The ARM version 6 architecture with ARM version 62 and beyond introduced the thumb 2 instructions. These are actually 32-bit instructions for thumb state, and the difference between these thumb 2 instructions and the ARM instructions is that there are no conditional execution in thumb 2 instructions. The advantage of having the thumb 2 instructions in place of ARM instructions that you do not need to perform a state switching from ARM to thumb or thumb to ARM when we want to improve on the code density of the instructions that we use. Now, ARM version 7 AR still maintains full ARM and thumb state support, so we can leverage the legacy code that has been developed for ARM state as well as thumb state. But ARM version 6M and ARM version 7M cores have only thumb state support built in, so meaning that there is no ARM state support in these cores, and they are targeted for embedded systems where the requirement for reduced code size as well as lower cost means that having a simpler architecture and simpler instruction design would be beneficial. And this allows us to streamline the processing without a state switch from 32-bit to 16-bit instructions and vice versa. However, this means that we would have to be careful of how we write the instructions, assembly language instructions in the first place. We cannot use conditional execution instructions in any of the source code if we want to be able to compile it for the ARM version 6M or ARM version 7M cores. Further information about the thumb state and other details of the thumb instruction set can be found in the references here. Well, we will look into how we can utilize these thumb instructions in the next session in part 2.